Morning. This is one of those days where I started at 7 a.m. and hasn't had a moment's break. I'm trying to remember what I wrote my lectures up on this. So we'll go over this. So I'm going to talk about, we're starting chapter 9, and these are the properties of the laser. And the key things are, what's the output power you can expect? So you will use this when you're designing your tie sapphire, or the formulas we come up with today. What kind of output coupler should I choose? How hard do I have to pump it to get so much power? That kind of stuff. So this is kind of technical, pragmatic issues. So I'll look at the simple case first, because that's the one I understand. And then I'll try and go into the semiconductor laser a little bit, which is something I don't understand very well. So that'll be dev deep. But we'll talk about those kind of things. On Wednesday, we'll talk about transients. Transients are messy, ugly. I hate them. We'll just do they're solving the rate equations with a step function. That's what it is. And we'll look at some of the funny things that happen in a laser when you transiently pump it. But that leads to really interesting things like Q switching and mode locking. So that'll be kind of the fun aspect. So this next couple lectures, we'll look at kind of some dirty details and get down into that. Let's start with some definitions. There's 3 or 4 level lasers. So we characterize the laser by how many levels it has. And the classic analysis is a 3 level or a 4 level. A 3 level, well, let's go back to the beginning. We talked about 2 level systems in the Einstein A and B. Remember we had this box and we had this 2 level atom here. And it was interacting with the electromagnetic field. And we showed that it was impossible to create an inversion in this. We found that even with infinite pumping, N2 is always less than N1. No matter what we do. The best we can do is equalize these two things with 2 levels. So with 2 levels, you'll never get an inversion. But we also know from all the gain studies we did that we want N2 minus G2 over G1, N1 to be greater than 0 to get gain. So we'll never get gain in Einstein's box here. So we need to introduce another level. So the first thing to do is just do a 3 level. So let me define one like this. You get level 0, 2, and 1. I'm going to try and keep 2 and 1 in level here. I'm always going to go from level 2 to 1 for lasing. So a 3-level system lets us do this. We've got a ground state, and the ground state is where all of the atoms are who are unpumped, unexcited. This is usually a giant reservoir of atoms. They're just sitting there, minding their own business. Then we pump some of them up, and typically we pump up not too many, but in this case we have to do a lot. So a 3-level system is I pump up to this state here. There's a state below which you can laze to, and then it relaxes. So here's laze, and here's relax. Now, one 3-level might look like this. Another 3-level might look like this. We pump, it relaxes to here, and then lazes here. Okay, now, what are the problems with this thing? Well, in this case, obviously, I want more atoms here than here. But this is my great, population of atoms just sitting here. So to get an inversion, to have more here than here, I've got to depopulate the ground state and get them all up here. And I've got to get more than half of these things out of here just to get neutral and then to get some gain on top of that. So I have to do an awful lot of pumping just to get rid of the absorption. If I don't pump this thing, I'm going to have a big absorption here. So I've got to lift a bunch up, put them there, and get it to come down. So this looks like, oh, let's do it this way then. So I'll just pump them up to here. It lays down to here, then relax. The problem here, we always like to have some fairly decent lifetime up there because we want to pump, and the total population, just in steady state is R tau. So we're going to pump and try and see some population here. Now, when I do that, I like this to have a fairly long lifetime. But if I got a long lifetime here, atoms build up. The pumping works both ways. And so if I start to build up some significant population here, the pumping starts to bring it back down, and I'm defeating myself. If I'm optically pumping, I get absorption, stimulated emission, does me no good whatsoever. So we typically don't like to pump up to our top level because the pump depopulates just as fast as it populates, and it makes life tougher. And it's hard to build up, if you have a long lifetime here, it's hard to build up much population because the pump will kill it down. And then it comes down to here, and then this is going to quickly relax, and it's hard to find a system like that. So we typically I mean, actually, I'm not even aware of a 3-level laser that looks like this. This is a hard one to find, but the problem is you like to have what's called a metastable state, a fairly long-lived state above in which you're storing your upper level, and this is hard to find. This is the more classic 3-level, even though it's got a big disadvantage. The Ruby, which was the first laser, was a 3-level, and in the Ruby, what you've got is you've got your ground state, and you got this big continuum of bands up here, and then a little guy here. So this was really nice because what makes the Ruby, you've seen a Ruby, it's nice and red, it's absorbing blue and green. So it's absorbing you're seeing the complementary color, so it's sucking all the blue and green out of the atmosphere. So it's got very broad absorption bands, which made it easy to pump because back then they just took a flash bulb and flashed this and just white light like mad. And so all that light went up and got absorbed, and then most of it relaxes down to this level. This is the E level. E, that's a spectroscopic term. And then it sits there, and this is a 3 millisecond lifetime, which is huge. It's just insane. That's very long. And so, but it made it very easy for this population to build up. So you're pumping, and these things very quickly, this is usually, this is on the order of nanoseconds or less, relaxes down to that level, and then it sits there forever. So pumping, it sits there for a while, so you keep pumping, and you pretty soon you depopulate that because it goes up and just hangs around for 3 milliseconds. So it's very easy to depopulate the lower level, create a gigantic inversion here, and then lasing would happen. Now, it turns out in this one that the degeneracy here was for Ruby, I think it was 2, I forgot. Anyway, it's, yeah. This had a degeneracy of 2. This has a degeneracy of 4. So you got to have N2 minus G2 over G1, so 2 over 4 N1 must be greater than 0. So if that was equal to 1, you'd have to take half this population, put it there to get it to be equal. And then after that, you start getting gain. Because it's equal to that, you only need to take 1/3 of this up, and then you've achieved your inversion, or you at least broke even. And then after a third, only a third. You only have to take 1/3 of it up. But you basically have to depopulate the lower level to make it transparent, and then pump a little bit more to get lasing. So there's a tremendous overhead in these things. You waste a lot of energy just making it transparent, and then after that you get to laser. But there are, the very first laser was 3-level, so they do exist, and we deal with it. The much more preferred laser is the 4-level. And 4-level is a generic term. Most lasers have lots of levels. But the 4-level are the ones we're worried about. You've got your ground state. You got the state you're pumping into, call that 3. It relaxes into level 2, lasers into level 1, and then relaxes back down to the ground state. That's a 4-level. Now, most typical lasers, like say neodymium or something, has probably 20, well, we talked about neon the other day. Remember, we had 20 levels. And so we're just talking about between any particular pair of levels, you can get a, this and that, you can get an inversion at a laze. So it doesn't just mean there's 4 levels in this thing, but these are the ones, you got 1 to pump to. Ideally, this is a very strong transition, and this is fast. And you want that fast so that there's basically nothing sitting up here at all, because the pump process works both ways. So you want to kick an atom up here, have it instantly drop out of there, so the pump doesn't interact with it anymore. You like this to be long-lived. We call it metastable. I don't know what that means, but you want tau there so that the atoms have a chance to build up and create an inversion. It's this thing here, the inversion is N2 times tau, or R times tau. And then the nice thing here is it drops down to this state here. This is way above the ground state. So its Boltzmann population is effectively 0. So this is effectively empty. And so as soon as I get 1 atom up here, I've got gain. And that's what's nice about the 4-level. And then I pump a little bit, instantly have gain. I don't have to worry about pumping half the stupid population up to get gain. So gain occurs immediately. And then in an ideal system, this is a very fast relaxation, so that when it comes down, this drops out. And ideally that stays roughly 0. And so now you've got a real nice clean system. So most of the good popular lasers, the ones that are efficient and so forth, most lasers are 4-level. And so, this might be near the ground state, but typically it's not a well-populated state coming down. So that's what 3 and 4 means. And we'll usually deal with 4-level lasers. There's a term called quantum efficiency, which you'll hear about. And quantum efficiency is the ratio, let me look here. Quantum efficiency is the ratio of the output energy to the input energy. So if this were an optically pumped system, I'd pump it with H nu pump. I'd extract H nu laser. And the quantum efficiency is the ratio. So eta is going to be the output energy divided by the input energy. So it's very simple when we're talking about optical pumping. So, and quantum means I'll put for one photon in, how much energy do I get out in one photon? And so, Ruby, I don't know the numbers. This is like 500 nanometers, and this is like 700. And so, since wavelength is inverse to this, Ruby is going to be something on the order of 500 over 700 for quantum efficiency. Okay, it's not too bad. We don't worry about the fact that it took us forever to invert the population. It's just the quantum. In something like classical, everyone's darling now is ytterbium. Ytterbium is a transition, it happens about 106. Its output wavelength is 1.06, and it pumps at about 940 or 960. So it's got a quantum efficiency of 0.96 over 1.06. It's about 94% or so. That's pretty good. So that's very efficient. Why is this important? It turns out in all the lasers now, when you start, back when I was a student, just making something laze was great. Now you want to make a product, you want to put it in something, you want to have a power supply, you don't want to have fans. So heat and cooling are always the limiting factor in lasers. So what you want to have is a system where you have a box and the amount of power going in is minimal, the heat coming out is minimal, and the light coming out is max. So you want a very efficient system because you don't like to get rid of heat. If you take a laser system and it's going to be, say, a LiDAR system on your car, you're going to put this on the roof of your Google car for LiDAR, you don't want to have to deal with a lot of cooling up there. It's a big hassle. If you're going to put this on an airplane as a jet for, scanning or something like that, you do not want to waste a lot of power, and how do you cool this stupid thing? Heating is always amazingly, heat is the actual limiting factor on most products now, especially lasers. So you like a very high quantum efficiency. So whatever doesn't go in light turns into heat, turns into phonons. So this relaxation here is heat. This relaxation here is heat. It doesn't matter if it's electrons in a semiconductor or if it's gas in a discharge. Whatever doesn't come out as light is going to somehow internally be converted into heat. And getting rid of that heat's a hassle. I once visited one of our alum, Dave Welch. He's the CTO of Infinera. They're one of the leading companies which makes fiber optic telecommunication systems. And he takes me in, he shows me his latest box. It's got a terabyte of communication. It's got these little laser diodes. It's got them all cleverly wired up. They're feeding a fiber. He's going to put a terabyte of information onto this fiber with multiplexing. And he said, "This is as fast as we can go. I can't go anymore." I said, "Why don't you put more lasers in?" He said, "I can't put a bigger fan on the box." What? He said, "The fan. I have only so many dBs of noise I can put in this room, and I have to put a bigger fan to get the heat out, and I can't put a bigger fan on." And here, I thought, this is nuts. Here we're talking about terabytes of information to send across the ocean, and we're limited by this stupid fan to get the heat out of this thing. And it's literally the issue. You got so many lasers there, they're drawing so much current, you got to keep them cool. And at some point, you can't pull the heat out fast enough. So that was the limiting factor in this high-tech heat of all fan size. So keeping heat down is nice. So things like this is an amazing system here. More typical Ti-Sapphire. It's gonna be more like 60 or 70%. Another issue with thermal loading like this. Let's say you got a Ti-Sapphire rod. I'm looking at the end of it. So the laser beam's going into the board. So here's your Gaussian beam, and we're pumping, unless we're pumping with another optical beam, which is perfectly matched. So everything's wonderful. I'm putting power in, I'm pumping it, it's relaxing, it's lasing, it's creating phonons, where? Right here. So we're getting a lot of temperature right there. If you look at the temperature profile in this rod, it kind of goes along, kind of like this, and then, and right in the center, you're generating a lot of heat. Okay, so what? Well, there's nothing, life is never simple. You have a dN dt. The index of refraction depends on temperature. And so now I've got an index gradient, which looks like that. And notice it's somewhat parabolic. Just first order. A parabolic N is a lens. So you get what's called a thermal lens. And so you build your laser, everything's cool, you got your ABCD, it's all stable. You turn the thing on, you get it lasing, you turn the power up, it goes off. Turn the power down, it turns back on. What the hell? Turns out you got a lens. And so your cavity, you had your two mirrors and you're all happy with them and everything's stable, but you forgot about that lens. When you pump this thing, there's an additional lens kicks in and changes all the focusing for you. So you got to worry about the thermal lens. Well, if you got something which has very little heat, it's not a big problem. If you got something which has a real bad quantum efficiency, you got a lot of heat, you got a problem. So there's lots of issues to deal with. And the quantum efficiency is one of these which you can't do anything about it. It's what nature gives you. You got so many atoms on the periodic table, you put them in the system, they do what they do. But you've got to deal with the consequences of it. Okay, so let's compute the output power of a laser. So this is a practical formula. And it's very simple. Now there's two ways to do it. I can do it exact and rigorously, or I can do it simple. And I'm going to do it simple because I think you'll get it. You'll see it. It'll make a lot of sense. The exact and rigorous form doesn't tell you much more. But once you see and understand what's going on, then the exact rigorous form at least makes sense. I could just put a whole board of mathematics here and have a result at the end of it, and I don't think you'd be any better off. So you can read in the book. The basic, it's called ridge rod analysis. And it's in the book. And you can go through that, and it'll kind of tell you what the power is and coupling and so forth. Does a very nice job. And it turns out this is what you need to do if you really want to get to that second decimal place. This will get you 95% there. That's good enough for us. So, and what I want to get is convey an understanding today and that kind of stuff. And it's real simple how this works. We're going to use two equations we've introduced a couple times. One is, I hope you know and love these two. The inverse, one is the one is the inversion as a function of intensity. And that's just given by whatever you do when you pumped it initially, divided by 1 plus I over I sat. So there's our inversion. And we have a lot of inversion, we get a nice gain, we pump it, then we saturate it and the gain drops, saturation. The second is the threshold condition. What's the minimum inversion we need? And that's just 1 over 2 sigma L, length of the gain. L is the length of the gain, not the laser in this case, times the log of 1 over all my losses. So let's say I got a R1, R2, T to the fourth, and so forth, whatever it's going to be. Those two equations are all we need to compute the output power. And the reason is because we've got an intensity here, so I'm going to solve for that intensity. And I know what my initial gain is, and I know what my final gain is. Remember how the laser operates? We put this system in between two mirrors. We have a mirror, we've got some gain and a mirror, we've got these reflectors and so forth. And initially the gain is greater than the loss, and so light builds up, the intensity builds up, and the intensity builds up to the point it saturates the gain until the gain is equal to that level. So N2 of I equals that when we're lasing. So now I know my initial gain, I know my inversion when I'm lasing, and I've got this intensity term here, so I'm going to solve for that. And that's going to tell me what the intensity inside the laser is. It's real simple. And once I got the intensity in the laser, I can figure out what it is outside the laser, and off we go. So it's pretty simple to compute these things. So let's think about this. Okay, so what we have here, this term, let's look at this term here. We got this term by putting a blob of photons here and just kind of running them around. And we said, okay, we saw a gain going through the crystal of 2 sigma NLG. That was amplification twice. We went through the end facets 4 times. So that's like 99.5 to the 4th. So that's what's retained. Then we hit 2 mirrors. We had an R1 and an R2, and that's retained. So this is what's retained on a round trip. 1 minus that is the loss. So 1 minus that thing will represent what's lost on a round trip. So this is the whole round trip thing. This term here, t to the 4th, R1, R2 is the physical. It doesn't represent the gain. It just represents what's retained by the mirrors. So this is the physical non-gain, physical retention, and 1 minus that equals the loss per round trip. So this is going to be some number, like these are all fractions. So 1 minus that's going to be a small number, maybe it's 10% or something like that. That's how much light is lost per round trip. Does that make sense? Now, let's look at this thing here. I've got this threshold condition. And it's got my length of the gain, all that kind of stuff, and then this log of 1 over this stuff. 1 over the retention. So I can write that as 1 over 2 sigma Lg times the log of 1 over 1 minus, I'm going to call that the loss. So this is equal to 1 minus the loss. Does that make sense? Now I'm going to assume I've got a system where I've got fairly low loss on a round trip. And that's going to let me get rid of this log function. My goal is to get rid of the log and get it kind of into linear space, because linear math is a lot easier than log math. Okay, so we make that assumption. And the only reason we're doing that is because I want to get rid of the logarithm. And under what conditions can I do that? Okay, so let's recall that the log of 1 over 1 minus x is approximately the same as the log of 1 plus x. And if x is small, that's approximately equal to x. This is the kind of math I like. I go from logarithms of inverse functions to x. This is about as simple as it gets. How accurate is this? So I'm taking 1 minus my loss. How big can my loss be for this approximation to be any good? So let's let x equal 0.1. Then the log of 1 over 1 minus x equals 0.105. So if x is in the order of 0.1, this approximation is excellent. Yeah, it's very good here. If x is equal to 0.2, so if I've got like 20% loss per round trip, the log of all this stuff works out to be 0.223. So it's pretty close. It's within 10%. If I've got 30% loss per round trip, this turns out to be 0.356. So my approximation is starting to deviate now. So I would replace this with 0.3. I'd be underestimating by about 15-20%. Still not too bad. So long as we're in the range where our loss is on the order of less than 25%, this is a pretty good approximation. Most, optically pumped lasers and solid state lasers and that kind of stuff will satisfy this condition. Gas lasers almost certainly. CO2 lasers usually. Semiconductors not even close. So this will not work for a semiconductor laser, but this analysis will work for most, optically pumped systems. So we're going to make this approximation right here, and we're going to replace the log of 1 over 1 minus L by just L. So that all this mathematic gymnastics we're doing is to simplify that equation. So we say that n threshold equals 1 over 2 sigma LG times the loss. And the loss now is my round trip loss. If I start with 1,000 photons in the cavity, turn the gain off, let them rotate back, how many are still there? 800. So I've lost 200. I've lost 20% of them. That 20% represents my loss, 0.2. So this is a fraction. And it's probably on the order of anywhere from 0 to 0.25. So it's a small fraction. But it represents the total loss in the cavity. Okay, if I multiply this here, 2 sigma LG N threshold equals loss. Notice what I've got here. I'm saying that my threshold inversion times the cross-section, all that kind of stuff, must equal the loss. This is the same as gain equals loss. That's your basic definition of when lasing occurs. How does an oscillator operates? The gain equals the loss. Everybody's happy. So this term here, I'm going to replace with loss. So all this math here would be just the loss term. Now, how about, let's see. We had this initial inversion up there. Before I saturate everything, I have this N2. We have N2 as a function of intensity, but we also have N2 and just the initial, this is my initial inversion before we start the laser. So I turn on the pump, I get this inversion. My gain, my open loop gain, my unsaturated gain is going to be 2 sigma LG N2 of 0. That's going to be the gain we experience in a round trip. I'm just going to call that gain. Call it gain. So that's how much amplification I'll get going through this crystal twice. And it's just a number. And I'm doing this so I can just kind of relate the two. So the inversion times cross-section times the length gives me my total gain. Got that? I'm going to plug those back into these things now. So let's look at my top expression there. I've got N2 of I equals N2 not over 1 plus I over I sat. Now, when it starts lasing, this becomes N threshold, right? So I turn the thing on, it starts lasing. When it's lasing, this is my condition. N threshold equals N2 naught divided by 1 plus I over I sat. Right? Now I'm going to multiply both sides by 2 sigma LG. All right, now what have I done? 2 sigma LG N threshold, that's equal to the round trip loss I have in my cavity. 2 sigma LG N naught is my small signal gain in the cavity. And so writing that in terms of G and L, we get, I'll just write it this way. We find that, okay, loss 2 sigma LG N threshold equals the gain divided by 1 plus I over I sat. So the loss in the cavity, unsaturated gain equals that. Solve for I. Now solve this for I. I find that the intensity in the cavity is going to be the following. Small signal gain divided by the passive loss minus 1 times I sat. And that's the equation I'm looking for. So what's the intensity inside the cavity? It's my small signal gain divided by the passive loss minus 1. Yeah?
So, notice you said earlier that the gain is equal to the loss, right?
Yes.
So, this is not...
So this is the unsaturated gain.
The what?
Unsaturated.
Oh,
This is, if I turn the pump on and I block the lasing, this would be my initial inversion before it saturates. So, and then this is the total gain I've created. Of course, we know it's going to saturate down to whatever whatever the intensity wants it to be. So this is the unsaturated gain. And of course, it's going to saturate down until it equals the loss. So this is going to be my final answer. So my intensity, when the intensity is this equal to that, then the gain is saturated at the loss. But what's nice about this, I know my initial pumping. So I say, okay, I'm going to pump it this hard. I'm going to run so many amps through this thing. So I know what my initial gain is. I look at my resistors or my mirrors. I'm still in 210 R. I look at my reflectivities and that kind of stuff, and I figure out my losses. And then from that, I know my relative amplitude there. I know ISAT. ISAT's just given by Mother Nature, h nu over sigma tau. I look at it. That tells me what the intensity is in my cavity. If I want more intensity, I got to create more gain or reduce the loss. But that's how it works. What is this intensity now? So this is a standing wave cavity, but it could be any cavity. Let's do a standing wave. Got a mirror and gain right here. So I've got a wave going this way and a wave going that way. And I'm going to call it I plus and I minus. So I've got a beam that's bouncing back and forth. As far as saturation goes, does the atom care which way the photons came? Is it going to saturate different from I plus or I minus? Any thoughts? No. It's just intensity is intensity. It's either it stimulates or it doesn't. And so inside this system here, the intensity inside the crystal is the sum of those two. So the total intensity in that crystal is what's causing the stimulated emission. It doesn't care who's doing what. So I've got two forms here. Now generally, if our gain is on the order of say 10 or 20% per pass, the intensity doesn't vary very much going across here. And then some of it couples out, comes back, builds up. So in the crystal, to a very decent approximation, I plus is roughly equal to I minus. So we can usually say, to a pretty good approximation, that's equal to 2 I plus. And if I have a huge amount of gain, there might be some difference, but that's a fairly deep, the I plus is equal to half the total intensity in the cavity. Okay, how much power is going out now? So typically we will make a laser which has a mirror which has predominantly high reflectivity. We'll call this the high reflector. And 99.9 or 99.5 is pretty easy to get that. 99.8 or 9 is you're spending some more money, but you can get it. So typically it's going to be less than 0.5% of the light goes through here. There will be a little bit. You can look and see in the light. You'll always see a little bit of beam coming through. Not much. But if I'll make one of these called the output coupler. And this is the one which we will adjust the reflectivity to be substantially below high reflector, so we get a good coupling here. Maybe this is 90%. That might be a good answer. So what happens is it's got a transmission. The transmission is 1 minus R. So what's my output intensity? Well, I've got I2 hits this thing. Some of it leaks out, the rest reflects back. So my output intensity, I out is just going to be I plus times the transmission of that mirror. And then the rest of it reflects back. I minus now is going to be what's reflected. And then I minus builds back up, and it reflects, then it builds it back up again, hits that, gets knocked down, and it keeps on going. So this is how the laser operates. You make 2 passes to extract the light, couple some out, send the rest back, and keep it going. So now I know what my output intensity is. It's proportional to I plus, but I plus is just twice my intracavity intensity. But that's just given by this. So now I know my output intensity. I out is equal to the transmission of the output coupler divided by 2 times my unsaturated gain divided by loss minus 1 times ISAT. So ISAT kind of sets my benchmark, and this is what fraction of ISAT comes out. So there is your first order description of what the output power of a laser is. And it's going to depend on your basically your unsaturated gain in this case. That's one, and your output coupling. Okay? Now let me make one vague statement here. It's all in terms of intensity. And if you really are thinking about this, imagine I've got a cavity which kind of looks like this. Or my mode does something really bizarre like this. Okay. So the intensities we're talking about are right in here. And yet I said my output intensity is transmission times all this stuff times ISAT. Well, we got to use our head here. Clearly the intensity here is quite intense, and then it spreads, it just physically spreads here. And it's much, so the intensity here is nowhere near that, just geometrically. It's much smaller. And so this literally isn't true, but it would be true if my output coupler was right here. So if my output coupler shrunk down right to there, then that formula would be correct. And my power would be equal to that, I out times the area of the beam, right there. So here the area is quite large. And so if I'm really going to compute that, if I really want to know what the power is here, what I have to do is say, well, here's my output intensity, but I multiply it by the size of the beam inside the gain medium. And that then converts my intensity into power. Now the power can spread all over the place. Then I take 10% of that and it comes out and they're all cool. So when you're looking at this intensity, it's not literally the intensity of the output. It's the intensity here within the gain medium. But we take those photons and they come out, and that's our power. Does that make sense? It's a subtle point. But when you look at this intensity thing, it's literally not the output intensity. We have to multiply by area to get the power, then it all works. Okay? Okay, so there we are. So now we know how to control the power, how to compute it, and that kind of stuff. So it's all proportional to the gain and T2. So T2 I can control. I can change the reflectivity. Now, it looks like I just want to make T2 big and I get a lot of power out of this thing. Well, I got to think about this. We said that we've got a small amount of coupling, so our loss is small. So T2 has to be small. I can't make T2 arbitrarily big. In fact, if you look at your output power as a function of the T2, here's T2. Here's my power out. If I make T2, if I have no coupling whatsoever, a very low loss cavity, that's great. I'll have a lot of intensity inside that cavity. Everybody's happy. But since I have zero output coupling, I get zero power out. Or I could crank T2 up, just make it bigger and bigger, and just give lots and lots of coupling. But eventually I'm going to get a point where the amount of coupling I've got exceeds the gain I've got. So if I've got like 50% coupling and my gain is only 49% per pass, I'm never going to reach threshold. So clearly there's a point where this thing's going to turn off here too. So there's no coupling gives no power out, but lots of intracavity intensity. Too much coupling, I don't even reach threshold. So there's going to be some sort of curve kind of like this. And so there's going to be a local optimum somewhere in there. And that's what we call the optimal coupling. Now in my experience, this is a pretty soft curve. So I probably should draw it more like this. It's more like this, And you've got a large range here. You'll compute this for your Thai Sapphire, and you'll all come in with your numbers, and then I'll say, that's great, I've got one coupler. I've got a 3%. Live with it. And it's not going to give you much difference. So it's a fairly soft function, but it's good to go through. So we can compute the optimum coupling by looking at this thing here. And what we do is you say, okay, well, here's my output power as a function of that. So I want to compute DI, DT, or DT2, and then set it equal to 0. And so that's pretty easy to do. And if you remember your calculus and have faith, it only took me an hour to get this right. You get that you said in that your coupling is going to be equal to minus the loss plus the square root of the small signal gain times the loss. It's a funny looking equation. Let's think about it. If my gain equals my loss, then this equals L minus L is T. So if gain just equals loss, then my optimum coupling is 0. I'm just right at threshold. So this clearly, I've got to have gain. I must have gain greater than loss for my laser to operate, and that's clearly enforced here. And so the more they make the gain, the higher it goes up. I think I made some here's an example. Let's say your round trip loss is 1.5%. That's not too bad, actually. That's fairly typical when you have a lot of surfaces and mirrors and stuff. And let's say the small signal gain is 15%, which for a tie sapphire laser is not too unusual. You get that kind of gain. So what's my optimum coupling? So you plug it in there, and you find your optimum coupling is 3.2%. So what you want, you don't want 15% coupling because you'll be at threshold. You have no intensity. The way this laser works is you want a lot of intensity inside this crystal to saturate all the gain. The more you saturate, the more conversion you're getting. Not enough intensity, you don't get any stimulated emission, it's all fluorescence. So you want to have a high intensity, so you want fairly tight coupling here. But this 1.5% loss, that means I'm getting stimulated emission, but I'm losing some photons here, I'm losing them here, I'm losing there. So this is stimulated emission, but it's going elsewhere. It's useless loss. And so what I'm trying to do is I'm going to try and dominate it here. So I'm going to get most of it into my output beam. I'm still going to lose some in other places. But the best I can do, this will crank the intensity up maximum, get the most stimulated emission, and still get more in my output beam than I could otherwise. I'm still losing it elsewhere. Ideally, I'd like to go back and knock this way down. If I can start knocking this down, more of it goes into my beam, everything's happy. But ironically, as I make this smaller, this will get smaller. And so I have more intracavity intensity, so I'm just stimulating the daylights out of this thing. The more stimulated emission, the more efficient I become. So that's how this all works. But that gives you an idea how to do this. So this is a good analysis, assuming our total loss is less than about 25%, because we did that log of X thing. So for fairly low gain, low loss systems, this works very well. And for most lasers, you'll find that works fine. Okay, what do you do if you got, say, a semiconductor laser? How are we doing? 5 minutes? If you got high gain, it gets kind of messy. I'll just kind of outline it. So for high gain, you have to be a little more formal. And we have to go back and look at this log term and more kind of extract it carefully. So the book goes through this. But remember when we talked about the fiber laser? We had this fiber laser, and we computed what's the gain in this thing. And what we noted was that the inversion depends on intensity, but intensity depends on distance. And so the inversion depended on where you were. And so we had to solve this equation here. We said, well, to compute the total inversion, or the intensity, we have to go di dz is just given by sigma n of z times intensity. And that became sigma, our unsaturated system, divided by 1 plus I over I sat times I. And that was a differential equation. So we expanded it out, got this expression for I, and we solved it. And we got that the log, here's what we found. The log of I2 over I1 plus, you remember this, I hope, 1 over I sat times I2 minus I1 was equal to the integral of sigma n2 of z dz. So here's I1, here's I2. So when we have a high gain system, the intensity changes so much going through it that the saturation is not uniform. And effectively what we did in this thing is we assumed we had uniform saturation. The whole population was just feeling it. Look at a semiconductor laser. You can easily, you got this little zone here like that. You can easily have a gain of 10 in something like this. So here's I in, I out equals 10 I in. mean, these things are just amazing. They're just light machines. They just gain like mad. And so this is not a situation where I can take the log of 10 and replace it by 10. It's just, everything goes nuts here. So you have to use this kind of analysis to compute how the intensity goes through, because the intensity grows, it saturates more of the inversion here than it did here. And so you get a very interesting rule here. So that's how we have to go about doing it. So to do this, what are we doing? Are we out of time? I think we are. Oh, we have 5 minutes? Okay, good. So let's look at a ring laser just for fun. Not that you'd ever make a semiconductor ring laser, but it gives you one pass through here. So we got this gain region here. We have I1, and we're going to come back around, and here we have I2, and we're going to make this thing self-consistent. So I've got I1 going in, I2 coming out, and we want to see if we can find a self-consistent rule here. So again, what we want to do is calculate what's the loss in this thing. So we've got an R1, an R2, and an R3, and we have losses there. So our retention on a pass is going to be R1, R2, R3. We've got 2 surfaces we're going through, and they always throw in a bit of loss. A lot of these things have intrinsic absorption. If you don't pump them, they just absorb some light. So let's put in a little loss there, e to the minus alpha L. Alpha is just the absorption coefficient for the light. This is the amount of light which is retained for one round trip. We typically have very high output coupling in a system with high gain. So I'm going to extract that out, and I'm going to rewrite this as let's be the output coupler. So this would be R1, R3, T squared e to the minus alpha L, 1 minus T2. So that's that there. And so what I'm going to have is kind of a physical retention, and I'm going to have a loss due to my output coupler. I've got useless loss, and I've got useful loss. Loss coming out the output coupler, I want it. Loss going everywhere else, I don't like. So I've got useless and useful. So that's what's kind of separating those two guys there. Now, on a round trip, for this thing to be stable, let's set this equal to, I'm going to call this S. This is the amount of light which is retained on a round trip. So I come in I1, I come out I2, I come back around, and when I get back to here, this intensity is I2 times S. This is the light which is retained on a round trip. So I had generated that much, I retained that much of it, and on a round trip, that must equal my input. So here's my steady state condition. So I've got lasing, so I've got the steady state condition. So I'm going to go back and plug that into here now. So I've got I2, and I got I1 in terms of I2. And so I can write all these in terms of each other here. And you plug that into here, and what you get is the log of I2 over I1, which is I2S, plus I2 over ISAT times 1 minus S equals sigma n LG. I'll just sigma n dz. So this is my self-consistent equation now. Here's my retention, here's my intensities. And so I get a slightly different equation now in terms of this S thing. If I solve for my intensity, like I did before, I told you this would devolve just into math. So we get I2 over ISAT equals sigma n, I'll do that, dz, minus the log of 1 over S divided by 1 minus S. Okay, so far, exact expression. Now, what I want to do is compute what's I2 on this thing. And okay, I think it's a good place to stop. So what we're going to do, we're going to compute I2, and then we're going to take the derivative of it with respect to T. And so we're going to optimize the coupling T, and we're going to find the output coupling there. So it's kind of a tedious way to show you that for this kind of system, we need a slightly different form of an output coupler. But you're going to find the output couplings on the order of 60, 70%. You know, very large output coupling. But that's the basic idea. So we'll stop there. We'll pick that up on Wednesday, and then we'll get into transients, all right?